All right. So, quick review of the psychrometric chart. This is the sea level psychrometric chart. We have dry bulb temperatures on the horizontal axis. So, this is a constant dry bulb temperature line. We have constant wet bulb temperatures. We have constant enthalpy for specific enthalpy lines. We have constant specific volume lines. And in addition to those, we can read omega or absolute humidity values on the vertical axis. And also we introduce the constant relative humidity lines, curved lines. And also this line here is the 100% relative humidity line or the saturated air line. So you read enthalpies here, wet bulb values here. This is dry bulb, relative humidity, specific volume, and omega. All right. Again, another review. You see wet bulb temperature lines, enthalpy lines, constant specific volume lines, dry bulb temperature, wet bulb temperature, and dew point. Okay, well, let's do this first using the psychrometric chart, then I'll show you how to do it using these. It's a simple heating from 15 degrees C and 45% relative humidity, right? So we're trying to find the final state, other properties in addition to 25 degrees C. And let me add something. If the volumetric flow rate is, let's say, 400 CFM, what is the heat transfer rate? And everything else, try to define everything. What is the relative humidity at the exit? Omega 2, specific volume, and I guess that's it. Maybe wet bulb. What is the wet bulb at the exit? So we are heating humid air from 15 degrees C, 45% relative humidity to 25 degrees C. Let's identify state 1. We know the dry bulb temperature and relative humidity. So what is omega for state 1? What's the temperature?
15.
15 is here. 45% relative humidity is, this is 50, this is 40. So somewhere right in between these two lines. So this is our state 1, right?
Mm-hmm.
So omega is, if I take this line a little bit higher than that, we're here. So keep in mind, it says, let's say 4 roughly, but this is grams per kilogram. So this actually is 0.004 kilogram per kilogram of dry air. So that is 0.004. All right. So that's the state 1. Simple heating to what condition?
5.
To what?
25, I think.
25. So this is 25 here. If I go up. So the important thing is to identify the process on this. How do I connect the two lines? It says simple heating. Simple heating means there is no change in absolute humidity. Well, basically omega 2 is equal to omega 1. So when omega 2 is equal to omega 1, the process is a straight horizontal line to the new state, state 2. This is heating. So heating from left to right because the temperature increases. Cooling is from right to left, temperature decreases. Whenever we have simple heating or simple cooling, it means omega does not change. If you have humidification or dehumidification, then omega does change. All right. So if for state 2, what do we have? Relative humidity is what? Would you say 25%? Right? Between 20 and 30, 25%. Let's read H1 and H2. What was H1? 28 is more like it, yes.
Yeah.
So it's around here. Let's say 28. And H2 around here, right? 3, 4, 6. 38. You all agree?
Yeah. So
that's enthalpy. We identified omega to be, so omega 2 is also 0.004. What else? Relative humidity, we did that. We need specific volume, V1 and V2. This line is 0.82, and this one is 0.83. I would say 0.82 2. And what is V2?
Somewhere near 0.85.
Say that again.
Somewhere near 0.85, maybe like
Yes,
0.85
it is.
or something.
Let's say 0.85, 2, 1, something around that value. Okay, these two things, I'm going to wait for you guys to tell me. Wet bulb 1, wet bulb 2.
Is wet bulb 1 about 9.3?
That's pretty good, accurate, yeah. I'll take your word for it. I'm reading, yes, around 9, yeah. Wet bulb 2.
Is that a little over 13 or?
Yes, a little bit below 14, that's right. Let's see, maybe 13.5. I think that's good enough. We'll check with East later. So write these down, these values. I'm going to ask, because I'm going to switch to, well, we didn't calculate Q. Let's do that before I switch to East. So the first law for this is basically what we have is this. You have a coil and you have your duct, air flows through the duct, state 1, state 2. So if you want to write, there's no work in, work out. There's only Q in by the hot water. So we're not considering the water flow here, just the heat transfer from the coil. Q dot in to the system. So Q dot for this heating is going to be M dot times H2 minus H1, and M dot is unit conversion. 400 CFM, we don't need to multiply by 60. Actually, you have to divide it by 60 to make it meters cubed per second. So 400 CFM times, what was the conversion? 0.3048 cube, that's meters cube. It's going to be per minute. We want it to be per second. So divide by 60 times 38 minus 28, which is 10. What is the answer to this? Correct me if I'm wrong. I got 1.89 kilowatts. Can someone confirm?
I got.
Okay, good.
So you gave us the volumetric flow rate, right? That's the 400. So wouldn't we,
400 is cubic feet per minute, yes.
wouldn't we need to divide it by the specific volume to actually get?
Oh, yeah. You're right.
I got 124 kilowatts.
So we forgot to divide by specific volume, which is 0.822. That was a good point, thanks, 0.822. And let me correct the answer. What's the correct answer? After dividing by 0.822, should be a little bit more.
2.3.
Yeah, that. So 2.3 kilowatt, write these values down, and then we go to ease. Any questions about this before we move on to ease? Okay. Do you need a little bit of time to run ease on virtual desktop? It is a good idea to actually do this step by step. I'm going to explain. I have this code. It's not a code, it's just a bunch of equations here. So let's start. If you need more time, just let me know. If you don't say anything, I'm assuming that you're ready and you're typing ease. Okay. First expression. Defining temperature at state 1, you can use the bracket 1, the bracket and number. At the end, when you run it, you generate a array table, right? And you can enter the unit in this format, capital C for Celsius. There are other ways to enter the unit.
You have to put the bracket around, right?
If you want to enter for which one? For the index or the unit?
The unit.
The unit, yes, it has to be within brackets. Yes. So the second line, RH for relative humidity, you can change it to feet. It's fine. If you type PHY, lowercase phy, EASE will recognize it as a symbol, Greek symbol phi, but RH is also as good. So relative humidity at 0.1 is 45%. There's no unit for this. You have to always, this is the next one, always enter a pressure. This is a sea level problem. We enter 100 kilopascals. Do not use the index symbol or bracket for this because there's no change in pressure. This is always constant during the process, and we do not want to treat it as a variable, right? So type like this, just P1. Then next one is calling specific volume. So this is how you do it. This is function info. Please mute your microphones. Function info. Click on function info. And you have to check thermophysical properties. Then in this box, check air H2O. This is for humid air properties, air H2O. And on the fluid side, you just get one type of fluid, and that's humid air, air H2O. So the property you want to call is specific volume, which is listed as volume only. Click on volume. So the pair of properties that we have, by default, it brings in dew point, but we have temperature and what? Relative humidity. For state 1, we have temperature and relative humidity. And type bracket 1, bracket close here. Do not click done, click paste. I'm not going to do it. You guys click, well, let me do it and delete it then. Paste. So this is the statement you get. Specific volume is called based on temperature and relative humidity. Okay, next is calculating volumetric flow rate, or actually converting volumetric flow rate from CFM to meters cubed per second. This is the syntax you use for unit conversion. It in its database, it has a lot of standard units. So 400 CFM times convert, in parentheses, CFM from unit, comma, meters cubed per second to unit. So from to, it will convert for you. Then we need mass flow rate, which is volumetric flow rate divided by specific volume. We already called specific volume. Right. So after conversion, V dot in this equation is already in meters cubed per second. Then let me bring this equation up. We want to enforce this equation. Omega 2 is equal to omega 1. We call this process simple heating. So now we need to call omega 1. Again, go to function info. You don't need to change anything, thermophysical properties, air H2O, and here, this is the property you're trying to call, humidity ratio, UMBRAT. Click on humidity ratio, and we have temperature and relative humidity. And keep this as index 1, bracket 1, and click paste. You get this equation. Next step called enthalpy. Function info, enthalpy. Change this to relative humidity. Everything else is fine. Click paste. State 2, the only given is 25 degrees C. I enter it. 25 degrees C. So we need a pair of properties to read the next of the properties. For H2, to call H2, you go to function info again. It's already on enthalpy. Two things you need to change. At point 2, we know temperature, but we don't know relative humidity, right? Point 1. What we know is humidity ratio because of this equation here. Omega 2 is equal to omega 1. This equation here. And we need to change the index to 2. Click paste, you get this equation. There's no need for calling V2, but I've done it anyway. You can call the properties. And then next one is calculating the heat rate. M dot already calculated times H21 is H1. We called H2, we called H1. And this last one is also not necessary solving this problem, but to show the value, I just called this relative humidity at 0.2. Keep in mind at 0.2, we know the temperature and omega to find relative humidity at 0.2. At this point, you can click run. Let's see how accurate we were. What was the Q dot we got using the psychrometric chart?
2.3 kilowatts.
Very good, 2.295. And this format here, this is interesting. So right click on this, you have one box for units, that's the main unit. Another box for an alternate unit, I typed ton, so it will show both for you. It's about 0.65 ton. I can change this if you're interested in IP units. I can change this to BTU per hour. And it will show the BTU per hour. Change it back to ton. Volumetric flow rate converted to meters cubed per second is 0.1888. And then let's go to the array table, enthalpies. How close were we with these two enthalpy values? I think we read 28 and 38, right? So more accurate is 27.22 and 37. But surprisingly, Q is pretty accurate because the difference is 10. In our reading, also the difference was 10. So that's what's important. Final relative humidity, what was the value we got? I think we got 24 something, right? So it's 24.2%. Omega, we're a little bit off in reading omega, 0.00481. It doesn't affect our calculation, but if we need to do any calculation using omega, our psychrometric chart reading was a little bit off. And what were the specific volumes that we used? 0.83 and 0.86. Okay. Any questions so far? All right. Okay, let me show you how to generate a psychrometric chart using these. Get this to move down a little bit. Okay. So this icon or the menu, property plot, click on it. You get this window. All right. So up here you have these options: ideal gas, real fluid, psychrometric chart, or brine. Click on psychrometric chart. Carrier plot is fine. Type your pressure. We used 100 kilopascals for this problem. Range of temperature 0 to 40 is fine. You don't need to change it Celsius. And the constant wet bulb temperature line and constant specific volume lines. If you want to change them, you can. You don't have to. And click OK. That will give you a base psychrometric chart. All right. Now, we want to show our states on this. You have to go to overlay plot. To be able to do this part, you have to run your program and have the answers for the solution ready. So here, x-axis is temperature, y-axis is omega, and we are going to use array tables, and we have only 2 runs, 1 and 2. All right. Add point labels, or sorry, legend items, and let's connect with a thick line.
Sorry, how do you overlay it?
This is the icon here.
Okay.
So the thick line color, blue color, and I change the symbol to this, and click OK. This is point 1, this is point 2. It shows the process on the psychrometric chart. From 15 to 25, it's almost 45% relative humidity down to about 24% relative humidity, and omega is constant. These are not omega values. These are the omega values. It's a little bit confusing. So this is the vertical axis that you read omega on the left here. Any questions? Okay. So specific volume, we use 0.822 and 0.85 for the flows. All right. Okay. Well, I leave this to you guys. Do you see this question? The exit temperature of air. You see my screen?
Yes, sir.
So, we go to, it's a simple cooling from 30 degrees Celsius and 60% relative humidity until it's saturated without any removal of humidity. What is the exit temperature? We go to 30 degrees C, 60% relative humidity, cooled until saturated. 30, 60%. So 30 degrees C, 60% relative humidity. 60% relative humidity. So what happens when we cool it down without any humidification until it's saturated? We go from right to left, and we hit this point. So I would say 22 is better than 21.5. 21, 22. Well, no, wait. So this is 20, 20.5. This is actually 21. Do you agree? 20, 21. Yeah, let's say 21.5. So the answer is 21.5. So another question: what happens after this? If I like, this is my state 1 starting here, and state 2. What happens if I keep cooling this stream of air beyond this point?
Will it just follow that 100% relative humidity?
Very good. Yes, you cannot go beyond this line. So what happens is that it will follow this 100% saturated line to any, depending on how much cooling you have. So if your enthalpy change is for the amount of cooling is between these 2 points from 72, 73 to 40, you will end up at a temperature of 14 degrees C. So moving beyond that point in that direction is not possible. So when you do cooling, the air becomes saturated here, and then it moves to the left along this saturated line. All right, so that's cooling and humidification in that case. So you have a cooling and dehumidification, cooling and dehumidification.
So do we still consider that condensed water as part of the system that gets cooled? Like, does it continue to lose enthalpy?
It's no. The psychrometric chart is for the humid air properties. So once the water is condensed, it's out of the air.
Okay.
So it is collected in a pan, and it's out of the system. It's not in the air anymore. So any mass of water vapor removed from the air in the form of liquid is not part of the psychrometric chart anymore.
But it doesn't really affect our mass flow rate because that's
No,
basically
dry air mass flow rate is not affected by this.
And that's
Dry
what-
air mass flow rate is the same. So for dry air, m dot A1 is equal to m dot A2. Like in this case, you have a duct like this, and you have a cooling coil with chilled water. Water enters at air enters at state 1, exits at state 2, and there will be condensation. So if you have a pan here, you have some liquid water collected here. Air coming out of this at point 2 has a smaller omega than air entering. And to calculate the amount of liquid water, you have to do this. We'll cover this next time, actually. M dot A times omega 1 is actually m dot of water at point 1, state 1, right? Minus m dot A omega 2, which is mass of water at point 2. The difference is m dot of water that is condensed. Does that make sense?
Yes, sir. Thank you.